Okay, so that's true. So that ends the fun right there. Now we can't talk about whatever we were going to talk about. Okay, we're going to go back to like the business where we were. I mean, again, I just want to echo, and maybe I said this sometimes to some of you in Physics 203 last semester, but I really mean it now. Like, I think you guys are really on top of this. I really on the work and everything. And maybe I'm saying that too, because maybe I'm more on top of your work than I was, but I'm really appreciating everything that's coming in. And I just want to say too, like, so some people are getting in the math methods homework, and some people, and it's great. And some people are taking me very seriously at my word. And there's like, some people have submitted some of it so that I could see it, and then they're going to submit some later. And that is totally fine. I just want to reinforce again, like, if you have submitted the math methods homework, then hopefully you got it back, I think, unless you just submitted it. And if you submitted the methods homework and you got anything less than a 50, hopefully you saw a note or something where I told you like what needs to be done for it to be turned into a 50, and that can be later. So I think we're on the same page, you guys and me. So if you have not turned in math methods, like, it would be a good idea to start working, especially today. I think it would be a good idea, but you're still not late or in trouble. Even though the people that have turned it in have been noticed by their maker, or not me. I mean, but like, okay, you get it. But you're not late if you have not done math methods. Let me put this another way. You might have noticed that I put a new homework in the stream, technically due Monday, called homework number 3, a heat hypothesis. Okay, that is the next homework. It's very similar. It's actually, it almost could have come before number 2, almost. Like, you're going to see hopefully today that homework number 3 is very much going to come. It's very much exercises that come out of what we're doing today and the next day, as opposed to the homeworks that I assigned. Homework 1 and 2 were meant for you to think about things, and then we talk about them in class. Like, they're hard in that sense. Homework 3 is a little bit more traditional, whereas by the time you get to it, hopefully you're sort of practicing something that you have seen in class. Why am I saying all this? I'm saying this because if you're like me and you saw homework 3 put into the stream, and you haven't yet done homework 2, if you're like me, that's super annoying and stressful. Like, to see yet another thing pop on the stack when you haven't done the other thing. And if you're like me, you might be thinking, wait, now I don't know what's going on. I thought he said I wasn't late yet. Now he's putting in homework 3. Like, does this mean I'm late now? No, it just means that I don't want anybody in this class ever to not have some physics to do when they're ready to do it. Okay, so homework 3 is the next thing. If you've done homework 2 or most of whatever, yeah, please give it a shot. Move on to homework 3, especially when we're done with today's class. You might feel it's not that bad to do. Blah, blah. But, and it's technically due Monday because it's the next thing. But I hope everybody's understanding what's really important is the sequence. Like, don't try to do homework 3 before you do homework 2. Do homework 2 next, and many of you still have to do it, and it is fine. You are not late. It is the next thing to do. But if and when you've done homework 2, then you move on to homework 3. I mean, so I hope, I'm just trying to keep things in order, and I don't want to ever intimidate anybody with the size of the stack or whatever. But I think I think that's clear, because a lot of you have turned in a portion of math methods, and that's great. So don't worry about homework 3 until you feel like you've finished homework 2. And like, it may even, and even though it's technically due Monday, like, I don't think we're going to be talking about it on Monday. So just know that. And the game things, I think everybody seems to be understanding them. I hope everybody understands that every single class from here on in, technically, there's a turn due a half hour after class, which every single time is a 5-minute opportunity to gain 50 points, but it's not mandatory. It is optional. And there's no concept of late. You can always retro any of them if you want. They just get harder to keep track of. So, but please, if I think at this point I could safely say every single person has done turn 1. So if you understand what it means to do a turn, at any point you can jump on this train and start turning them in, if that makes sense. Okay. And someone in the other class asked me, so I will open another portal for anytime anybody shows video. I will definitely get, like, again, that's not to punish people who don't or whatever, but if you show video for 5 minutes and you remember and I haven't opened that yet, but I will, that'll be like 75 points. Okay. That just because someone else in the other class asked for that. Good idea. And if you come up with something else like that, I'll do it. Okay. But I think, is there anything else I'm forgetting? I think those are like the bookkeeping. I think those are the bookkeeping issues for the moment. And I'm ready to start going back just to the straight math that we're doing. And so that I'm about to go right back to where we were in these differential equations that we were solving Monday. That's what I'm about to go back to in the board. But I'm going to pause for a second. Are there any questions and again, I'm sorry I'm late today. But are there any questions or logistical concerns or grade concerns or anything like that? Or going what? Okay, going once, going. Okay, so I'm moving on. I'm moving back to differential equations. Yes, okay. So where were we? Okay, so where we were, just to remind you, like in principle, first, well, all of this is in the context of question 9 from homework 1, right? We are still on the last question of the first homework. And that's the way it is. Like, that's why that was the first homework. There's a lot going on in that question 9 of the first homework. All of what we're talking about right now is still in that context. What you find when you start looking at homework number 2 and homework number 3 is they're trying to unpack all the details and zoom in on all the details of what we're discussing right now. But for the record, we have still not finished question 9 of homework 1, and we will. What happened though, just to remind you, is we hit a differential equation. Like Hooke's law, the physics brought us to suddenly stare at what I'm calling a differential equation. And in fact, technically what we were looking at was a second order differential equation. So what we did, again, just to remind you, put this in perspective, is like last Wednesday and last Monday, we did a side road. We started a side road to look. First, we looked at something like dx over dt equals some constant times t, like not what I have written here. Just remember, first we did example 1 where it was like dx over dt equals 5t. And we did some stuff and we solved that and we got an answer. And it was like hard, but it was whatever it is. And we got an answer. And by answer, we mean we got some expression for x as a function of t. Like, that's the kind of answer we were looking for and we got. Then Monday, then we switched to example 2. This is all still like a mathematical instruction as to how to deal with the physics of question 9, homework 1. But we then said, okay, what about dx over dt equals some constant times x, right? That's what we were dealing with on Monday. And we did the same procedure, but we got a different answer, a very different kind of answer. And I'm noting that this second example, even though all we changed was a t to an x, that actually meant we were changing from some thing that had a derivative in it to an actual proper differential equation. Again, what makes something a differential equation is if the derivative is a function of the dependent variable rather than the independent variable. And so then we solve that on Monday. Now that's still a math exercise. Like, we're still saying, oh, the physics forced us to deal with differential equations. So now we're taking a side road and looking at the math of differential equations. And we solved our first one, like ever, on Monday. We did solve it, okay? And so of course we now want to come back to the physics and see if we helped ourselves in any way. Like, did we figure out anything that we can use here for our current situation? Well, yeah, what I want to say, and that's what we're going to do. We're going to see if we can apply what we did to the physics here. That's obviously the purpose of it. But I have to be but this is some murky territory. This is not easy territory. So I want to be as clear as I can and say, okay, really what we did on Monday with that differential equation, we did a method that you could look up in any book or on the web called separation of variables. Technically, we took a first order homogeneous, technically it's called a differential equation. And when we separated the dx, we put the dt, we multiply both sides by dt, and separate. That's like a thing that's called separation of variables. Okay, so that's a method. So technically, we just learned that method of solving a first order differential equation. But here's it was worth focusing for me, to learn that method. But we did that method, we did that separation of variables method in order to come up with our conjectured answer. Like, this is the very important part, okay, of what I want to say right now, that I made us all do that twice, like multiply both sides of an expression by dt to get somewhere. We did it first in the dx over dt equals 5t, then we did it in dx over dt equals 5x. That method we did twice. It's important enough to have done twice, but it's also misleading enough that I have to say that's not the main takeaway. Like, I want you to know that method, we are going to use it again sometimes, But the hugest takeaway is meant to be this, that method just got us a possible answer that we had some confidence in. Maybe even some of us were sure it was right. But the point is that we had an answer. That method gave us something to work with as a possible answer. And it only became our answer. It became our actual solution to the differential equation once we checked it, once we verified it by differentiating. I mean, that's what I'm trying to say on this page. Like, and this is an important subtlety, I think, because again, like since we're really in calculus land now, and we all know that we all have mixed feelings about calculus. I mean, I think people have mixed experiences and feelings and mixed confidences with calculus. So let me say this: in calculus, there's like differentiating, right? And then there's like integrating, which often looks like, which is like differentiating backwards in some respects. But if you've ever thought in the back of your mind, if you got sort of comfortable with differentiating and you sort of, even if you didn't perfectly, you felt like you could do it and you could do it right on tests and take derivatives. But then if you ever felt that once the integrals came along, that's when you started to lose it. Like, first of all, that is definitely me. If it means anything, I'm not saying I understood derivatives immediately either, but I got to a point at some point where I was like, I can take a derivative if they ask me to. Like, I can do the power rule. I could do the trigonometric derivatives, like the derivative of sine is cosine. Okay, I can memorize that. And like, it got to the point, for me at least, where once people said the exercise here is take this function and take its derivative, even if it was really complicated, involved a lot of chain rules, I knew, okay, there's a formula that I'm supposed to be following here that hopefully I memorize, and I'll do the formula and it'll work out. But with integrals, when they asked me to do integrals, if they say integrate this, like, unless it was like really exactly what they had told me the day before or something, once they started giving me integrals and say, do this, especially once it got into like integration by parts or like trigonometric substitution and stuff, let me tell you, first of all, if it started to become a fog for you, once math looked like that, you're definitely not alone. It definitely happened to me for sure. Like, I almost gave up when it came to integrals, like for real. But here's why I'm getting at this, not just to like psychologically comfort you, but the thing is, you're not crazy if you find integrals at all harder than derivatives. You're actually getting something important if you do, because this is my point. The truth is that derivatives are algorithmic. Any function that is well behaved or continuous, so to speak, any function that's like normal, that's not crazily made up just to mess with your mind, you can take derivatives of it. There's a procedure for taking derivatives of any function that is continuous and well-behaved. And like, there's an answer. And even if you forget how to do it, you can look it up. But with integrals, it's not that way. It's not you and it's not me. The reality of integrals is that integrals, when you have a function that you want to integrate, there's not a clear procedure. There are techniques and tools that we learn from experience. And some of us get faster and better at trying some tools that we have some reason to believe will work. But it is puzzle solving integrals. It really is, to the point where you can easily come up with a well-behaved continuous function. Like, one can easily come up with a function that's not crazy, but for which there is no integral. Like, integrals don't always have answers. You may or may not, some of you may realize that. To integrate something is not a cut and dried thing. It's something, so you don't even know when you start whether there even is an answer to an integral. I mean, this is in reality. I mean, if you're doing research or whatever. So integrals are actually harder. Doing derivatives forwards is like a procedure. Doing derivatives backwards is more of an art, so to speak. And that is definitely then true for differential equations. We are trying to run derivatives backwards here. And we need to know from the start that even in the cases that seem somewhat straightforward, like last week's, even in those cases, there's no hard and fast rule for how to do a derivative backwards. There's different rules for different situations, and some situations don't work at all. And you can't even know in advance if you're in one of those situations or not. So really, this is where study and research and art. So solving differential equations is like actually a thing. It's not something that a computer can be just programmed to just do automatically, the way a computer can be programmed to do derivatives, okay? So what all of this means is that any technique that first of all, this is also why I think it's just as good to learn this stuff in a physics class as a math class. So like, it's like wherever you can learn it, if you can learn, because it's an art, not a science. But in the physics context, The real thing I'm saying is we separated variables Monday and Wednesday to solve the problem that we tried to solve. And we're going to solve a new problem today. And obviously I'm going to build a new problem from that problem. But we're not going to use separation of variables again for this case. We'll use it later. Don't get too tied down to that method. What I want you to get tied down to is that the reason we believe the answer that we got, for that second problem, dx over dt equals 5x for that one, we ended up getting x equals 5. We ended up getting x equals like 7 times e to the 5t, right? Like that's what we got. But why do I believe that? I don't believe it because of our separation thing. Our separation of variables thing was just a road to get that thought in our head. The reason I believe that thought that was in our head is that we tested it. And I'll show you right now that so here's what I'm saying right here. I'm saying, and I should also say, I'm trying to get more physicsy, but I'm also trying to get more mathy in the sense that I don't care about the number 5. I don't care about the number 7. I mean, I love number 7. Like, don't get me wrong. Some of my best friends are number 7. I love number 7. I want to hug it and squeeze, but I don't literally care about it in that right? All I care about 7 in this physical context is that it's an example of an arbitrary constant that I could call 7, or I could call 5, or I could call the letter A, or I could call squiggle, as I'm going to right here, just because we want to get comfortable with letters standing with numbers. So, like on Monday, by some separation of variables method, we ended up guessing, okay, we think the answer, I'm talking about the answer, what the problem I'm talking about, sorry. Okay, I gave you dx dt equals, I said 5x. Now I'm just calling it squiggle x because I'm trying to say it doesn't matter what the 5 is as long as it was just some number, right? I said, what's the solution to d equals squiggle x? And we like did some algebra, and then we were like, oh, we think it might be like whatever x is at the beginning times e to the squiggle t. Now you might or might not have followed how I got that, but that doesn't even matter. What matters is that once I was it matters, but once I was believing that that looked like a good answer, the key is that I can verify, because differentiating, going in that order, always is a clear procedure. So now that I have something that I think is the original function, if I take its derivative, like follow chain rule, follow the exponent rule, if I end up getting back, if I take its derivative and this is the step that always, is very easy to forget. Like I take the derivative. So I'm literally just taking what I think my solution is, x equals x naught e to the t, and I differentiate it. I take the derivative with respect to t just by following rules. So by following chain rule and following the e rule, I get dx dt equals blah. So I'm reading right here, equals blah x naught e to the blah t. Now that looks like a blah mess. That, like, what does that tell me? So who cares? But if I remember, and again, this is the part that people always forget, if I remember that this entire thing here, x naught e to the blah t, all of that was what I was conjecturing to be called x. If I substitute x for all of that, then, right? So if I just call that x, then I realize, oh yes, it checks, because here that brings me back to my original differential equation, dx dt equals blah x. So what we always do, it doesn't matter how we get our possible answer. We have to adapt a different technique to different situations. But once we get a possible answer, we differentiate it, we substitute back our expression for the answer, and we can see if our answer is actually right or actually wrong. And if it's right, we're good. And if it's, one last, and then if it's right, we're good. But then we use it to solve for any arbitrary constants. Then we get the rest of the details if we have to. And if it's wrong, we might, now that we know it's wrong, we might see what the problem is and what to improve and how to make it right. So the really important thing is not how you get a guess, it's that you have a good guess to work with by checking. So that's what we're going to do today now with the differential equation that actually faces us in the physics. And again, please remember, this is actually what happened in the history of physics. The people that had to solve this is what we do all the time in physics, is solve differential equations. And none of the people that was originally doing this ever had a math class called differential equations. They were making this up to do this, and which I think is actually the more natural. So that's what we're going to do. So yeah. So we're going to apply this type of reasoning to the DPQ that's prompted by the physics. And now, why we have to spend so much time building up to this is that it happens. We did a practice. We did a first order differential equation. Yay. But now this physics equation that's facing us, oh my God, is a second order differential equation. Okay, so we're going to step up to this now. And again, I didn't want it to be second order. I didn't add, I'm not it just is, like, just nature just spat out a second order differential. So the left side of what we have here is one step more intimidating, or one step more advanced than what we had Monday, because it's a second derivative. But please notice that the right side of what we're, so this is now physics, right? This is back to now homework 1. And what this really is also, it's physics. When I say it's physics, what I'm saying is this thing that looks really mathy. That blue thing that looks so mathy is just a mathematical way of saying Hooke's law, assuming in our mind that we know that F net equals ma as well. So that's just the nature of a spring written mathematically right there. And as intimidating as it might or might not be, notice that the right side is exactly like the example we just did Wednesday. Instead of 5, we have negative k over m. But k is a constant, m is a constant. They happen to come from the physics, so there are 2 different constants, but you divide one by the other and you have a constant. Multiply all that by -1 and you still have a constant. Like, nobody said on Monday that the constant, the 5 or the 7 or the squiggle, that could have been a negative number. It just like happened not to be, right? So what we have here on the right side is a constant times x, just like Monday. We do know it has to ultimately turn out to be a negative constant, because that negative sign comes from Hooke's law. It comes from the fact that we have a restoring force here. So something's going to oscillate back and forth only because it's only always being pulled toward equilibrium. It's always being pulled in the opposite direction from where it's displaced, or from how it's displaced. So there is a negative sign here, but -1 is a constant. So we're still in the land here. We're talking about, we're given a situation where we don't know x of t. We want to know what's x as an expression of t. Unfortunately, what we do know is the derivative of x with respect to t. Like, we want x as a function of t, but we have the derivative of x with respect to t. And sadly, what we have about it is its dependence on itself, on x. So we're going to do what we did Monday. We're going to try to come up with a guess, and then we're going to verify the guess and solve for the constants. In that sense, we're going to do exactly what we did Monday. But I'm going to come up with the guess in a slightly different way now, because, in fact, that separation of variables thing, which I did teach for a reason and which we will need later, and it is like a life skill if you live my life. But again, the actual separation technique, that's not what we're going to do here. We can't, because d2x over dt squared means derivative of derivative. It doesn't mean derivative times derivative, right? So we can't, like, there actually is no direct way to just multiply both. We can't multiply both sides by dt and then multiply both sides by dt again, even though it looks like we could, because it looks like we have like dt squared in the denominator, but we don't really. That notation, and some of you might have wondered, in fact, every year, like, usually one person asks, like, you may or may not have wondered in your mind, why are second derivatives written in this clunky, weird way? Like, why it seems inconsistent the way we put the exponents 2 and 2 in the numerator and denominator. It's actually for a reason. It's because the second derivative is an operation being performed on an operation. It's really the derivative with respect. So what I'm trying to say right here, it's d2x dt squared really means the derivative with respect to time of dx dt, or put another way, the derivative with respect to time of the derivative with respect to time of x. Like that, that's why we shorthand it as like d squared x over dt squared, because, right, but the squares don't really mean square, they mean do the operation twice. Okay, so we can't just so it's not going to, if it did work I would do it, but I can't just multiply both sides by dt squared here. I'm going to have to do something different. Okay, what am I going to do? Well, I'm going to say to myself, oh, this is annoying, Because it's a second order. Why am I even dealing with second order? Oh yeah, because I'm a physicist. I'm not a mathematician. I don't actually care about them. I'm not trying to put everybody through a whole math thing. I care about, yes, I am secretly, but I care about the physics. That's why this equation's coming up, because I care about the physics. So maybe I can use physics to somehow unpack this thing. That's what we're going to do. We're going to say, oh yeah, we're trying to understand Hooke's law here. We're trying to get x as a function of t for Hooke's law. So why don't we picture what might happen or what did happen if we were in a lab? Like, because it's science, not math. Let's picture what would happen if we were in a lab or in a Zoom class with a simulated lab on a computer screen. Okay, getting abstract. But like, let's picture what would happen if we had a mass going back and forth on a spring and we wanted to know for any given moment in time, where is that mass? Like, that is our question, right? So let's just picture if we were doing that in a lab and we were letting a mass go back and forth, and we took a movie of it, let's say. And in the movie, we had also a stopwatch or something in the movie or something. And then we watch that movie and slow it down, or maybe put it into Logger Pro or some kind of like data analysis like software package. If we're picturing a movie of a mass going back and forth on a spring, and we imagine, like, say, every 2 milliseconds or something, like we slow the movie down so we can do this. If every 2 milliseconds we ask whatever, every 2 half seconds we ask, okay, where is the mass? Like if the equilibrium position is called 0 and there's some like meter stick underneath it or something, if we literally just took data and every 2 milliseconds and wrote down where the mass is every 2 milliseconds, we would get a table of values if we're experimental physicists. And then we would take that table of values, t and x, and we would make ordered pairs, data points out of those tables, and we'd slap it on a graph and we'd get a scatter plot. And I'm going to maintain to you, I would have asked you this, but since I wasted a little time being late, I'm going to submit to you that if we did that, and by the way, of course, that is what you're doing in lab 1, in a way, in lab 2, although to be fair, you're taking different data. Like, there's a reason that you're it's not a coincidence that we're talking about springs in lecture and you're dealing with springs in a lab. But to be fair, it's true. In lab, you're looking at you didn't literally do what I just said. Sorry. You took different data in lab 1, but since you played with springs, I'm hoping that you can picture that if you had a spring going back and forth and you literally just tracked where it is as a function of time, then I submit to you. Oh, wait, oh, sorry. Oh, yeah. Okay. All right, you can copy. This is what I'm just saying. Well, this is what I just said. If you want to, I'll pause for a second if you want to copy this down. But yeah, I'll just pause for a second to copy this down. Okay, sorry. I just lost. I think, did my board just? Sorry. That doesn't help you if my board just did. Oh my goodness, what did happen to my board? Oh, excuse me. All right. Okay, I've temporarily lost my board here, but so you can't copy it no matter what. Maybe I'll ask you. Okay, I guess I will. What I'm pausing on right now, where we're going with this is, I'm asking any of you to think for a second. Can you? And of course, I'll put this on the board as soon as it ignites. But picture axes. Picture T on the horizontal axis. picture, or maybe even draw this, please do, I guess. Draw two axes, put t, time, on the horizontal axis, put x, position, on the vertical axis, right? And imagine that this is, and so time is in seconds and x is in meters or centimeters or whatever. And imagine that this is a graph a scatter plot. Imagine a scatter plot of data taken from a nice, well-behaved Hooke's law spring going back and forth, back and forth, back over a long period of time. Like if your data was really, really good, right? If you took a lot of measurements and you didn't drink a lot of coffee, and the spring didn't do anything weird, could anybody either describe in words or put in the chat or in a screenshot or something like, can you picture what this graph would look like if you took reasonable data of a mass going back and forth along one axis, back and forth, Like, could anybody sort of give me a shape? Oh, yes, yes, well said. Oh, wait, sorry. Yes, good. Very good. Sorry, I don't know what's going on technologically here. Sorry. But yes, what I saw, oh my God, my computer, what I saw in the chat is trig function. I think there's more than one. Yeah. Oh, or wave graph. Okay. Yes. Like but I would agree with both of you if this is what you mean. I think where's my board? What's going on? This is so sad. Why is my voice changing? Welcome to my bar mitzvah. Sorry. Yes, I'm saying we might be boardless here, but I'm agreeing with Ardell and Amanda that I would think you would get something that would look, yes, like a trig, like a wavy, wiggly, trig functiony thing is what we would get. And in fact, I'm going to ask everybody to please draw that on the paper since apparently I can't draw it yet. But yeah, you would get an up and down thing like a sine curve or a cosine curve. Right, absolutely. And I'm not trying to be big. I'm not trying to absolutely a trig function. But the first thing, yes, a sine or cosine graph. That is what I'm saying. Now, but I would say there's advantages and disadvantages of the way that, like some of you were saying trig function, that's completely right, or sine or cosine, and that's what we're getting into. But I have to say, I also like the way Ardell put it for a specific reason, which is, I hope I can convince you that graph makes sense, that you would see that wiggly cosine or sine graph, I think, even if you never took a math class and never knew anything about sines or cosines, right? I think you could imagine getting that wiggly graph or seeing that it's right, believing it, even if you don't know anything about, like, in other words, I think the data would show a wavy, like Ardell's saying, like it would be a wavy, wiggly thing just because that's what's happening. The thing's going back and forth and back and forth. So on an axis, if its position is being notated on a vertical axis, then you'll see it going up and down the vertical axis as time extends. So again, this is all in agreement, right? But the reason, and so like a nice symmetric, smooth, wiggly thing makes perfect sense to guess or conjecture, because it's the simplest shape of wiggliness that we can imagine. In other words, I'm just trying to emphasize, it's going to turn out to be very important that we recognize that wiggly thing as a cosine or sine function. But I want buy-in that, like, we don't have to know about cosines or sines to believe that that's the shape of the graph. I think that's the shape. We would just get back and forth and back and forth. I might even, if I didn't know anything about anything, there really is something wrong with my, hold on, I'm going to have to, pardon me for a second. I'm going to have to plug this board in a different way. But to make this point, and again, I have to emphasize this because we're trying to figure out math here. We're not trying to do math. That's hard enough. We're trying to figure out what math to do this. So that's, of course, scary, but of course, that's the real way of science. And so what I'm trying to convince anybody is that if you can picture that a mass going back and forth, if you made an XT graph, I'm saying that I agree with Ardell and Amanda and Isabella and maybe one other person, that I think even without walking into a laboratory right now, I'm pretty confident that if I took good data, it would look like up, down, wiggly, wiggly, wiggly. And in fact, to be really, well, yeah, I think it would. Because the only other thing I could think of that might even describe that data would be like a sawtooth, would be like, would be like jagged lines going down diagonally, then up diagonally, then down. Like maybe someone of you might think the graph might look like that, because that's even a simpler form of back, forth, but it won't be a jagged sawtooth thing, because that can't happen in nature. You would never get data to suggest that, because every one of the corners in a sawtooth jagged thing, every one of those corners would represent a moment in time where something changed its speed from some high, changed its velocity from some really, like if you picture a sawtooth graph, every corner means that something was going like 30 miles an hour in one direction, and then instantaneously, like taking no time whatsoever, like a cartoon, just suddenly changed and started going 30 miles an hour in the other direction. That's what corners on a sawtooth graph would be. And that cannot happen in the real world. Like if something is going to change direction, if it's going 30 miles an hour in one direction and it's going to change direction, it's going to have to slow down 29, 28, 27, all the way to 0, and then go into higher and higher speeds in the other direction. So in other words, the only possible way something can go back and forth naturally, actually, is to do so smoothly and continuously. And that is what we call the cosine or the sine curve. Like, is that just that smooth, continuous, symmetric pattern, up, down, wiggle? That is definitely, that is the simplest way to picture oscillation in graphical form. Now, again, I'm really struck. Now, so I'm agreeing with everybody, and I'm struggling to do this without drawing, but I'll say one next issue. So we're going to guess. Our first guess here is that our answer to this differential equation, we're not going to guess like X, we're not going to guess a power function like we did with the first differential equation, and we're not going to guess E like we got for the most previous differential equation. We're going to guess something like sine or cosine, because of what we're all saying right now. And again, remember, hopefully you're somewhat convinced that this is a reasonable guess, but that's all you have to be convinced, is that it's reasonable, right? I am not pretending at all that any of us have proven anything yet about this, but all we need is a guess to work with and check. So I'm thinking we're going to guess that our answer is some kind of sine or cosine. Now I'm going to go one step further and say, I even think we have good reason to guess one rather than the other. Like sine and cosine are super similar, and certainly anything that you express as a sine, you can figure out a way to express as a cosine, vice versa. So either one ultimately, if we're careful enough, will work. But I'll recommend that in this case, I'm going to say cosine is the better thing to guess than sine. And while I try to plug in this board somewhere else, I'm going to ask you guys to think for a second, put in the chat or tell me or voice, why? Now they both ultimately would work, but why am I saying cosine is maybe a little bit more? Yes. Well, yes, but no. I mean, yes. Wait, yes. Isabella's like reasoning is exactly the right reason. But I think you said it's the other way. It's because it doesn't start it. Like that is the reason. But I think you mean. Wait, I'm going to pause for a second and plug this in. But like, good. Hold on. What is going on here? Okay. Sorry. Okay, the board is like warming up again. There will be a slight pause on the board, but yeah. Okay. So the whole issue of 0 versus 0 is the issue. That is totally the right way to answer this question. I think, with all respect, I think maybe. So I think sine actually starts at 0, 0, right? I think that the sine of 0 is 0. So if I make a sine graph, that's the one that actually starts at the origin. And again, this is terrible that I'm just like talking about this abstractly, but there will be a board again soon. Or if anybody wants to do a screen share, if anybody feels like they know what I'm saying and wants to like do a screen share or something, like please, like 75 points, Nook Miles, the word Heaven's Gate. But I believe that sine starts at 0, 0. And that the reason I agree with Isabella that we want cosine here is because our situation here, like our mass, when t was 0, our mass was at 15 centimeters in the particular example of homework 1. And of course, 15 was just an arbitrary number. But in general, anytime we're talking about a mass going back and forth, oscillating, I actually believe we're always assuming that the mass starts somewhere that isn't 0. If by 0, we mean the equilibrium position. Because if we did start the mass at equilibrium, nothing would ever happen. It would just stay there. Like that's the nature of equilibrium. So actually, for any of these harmonic oscillators that we're now talking about, I think we're always assuming that the oscillator has an initial position, x naught, which then leads to all the motion and everything. So the reason I totally agree with Isabella, I like cosine because the cosine of 0 is not 0. Like the cosine of 0 is 1. So the cosine graph doesn't start at the origin. It starts with a positive y-intercept. And I think that is what we're talking about here. Something that starts somewhere. Like, remember, our y-axis is positions, technically x positions. We're here picturing something that starts somewhere on that axis, like not at 0, and then starts moving towards 0. So it like falls down. Again, I wish I were drawing this right now, but I'm not. Falls down towards 0, then crosses the equilibrium and keeps going, gets to the other side, and then starts coming back, right? So I think what we're talking about here is a cosine graph. And I also, again, think that soon I will start drawing, but is everybody good with, for me to, are we good with, and does that make, so we're guessing, thank you. I appreciate it. Totally see that, Ardell. Thank you. All right. So what we have so far is that we are guessing cosine. You know what I'm going to do right now? This is a weird thing. I'm going to right now pause for a second because this is getting just mathy enough. I don't think it's good for me just to be talking in abstract. I'm going to put in your Google stream right now class notes that you can look at. Like I'm going to put in the things that I would be showing you on the board just so that maybe you could at least see them. Hold on a second. Oh, wait, no, I can screen share it. Hang on. I'm sorry. Hold on. But where we are right now is we are conjecturing. We're guessing that our answer, remember, we're looking for x as a function of t. Right now, as what we are guessing is that x is some kind of cosine function of t. Like it's just a guess. You have to verify it. But it's not even a complete guess yet. We're building our guess. Right now we're saying that we think the shape of our guess, so to speak, is a cosine shape, or like the form or the type of function is cosine. There are further details that we're going to have to fill in even before we can guess this thing. Aha, I think I have it. And the details. Okay, pause. I'm going to put this in the. Yeah, please bear with me for a second. Huh. Are you kidding me? Oh, it's not even, sorry. Oh. We're almost there. Well, all right, I'm going to keep talking for a minute. I think the board is coming back. My backup plan is not going to work. But what I'm saying now, and if you were writing things down on the notes, what I would say is what we know right now. We don't know. Don't write down x equals cosine of t, but do write down, please, x equals lowercase f parentheses cosine of t end parentheses. Let me just say that again. I'm just trying to be as clear as possible. Like if you can, in your notes, please write down, like what we have established thus far is x equals f of cosine of t, like lowercase f, parentheses, cosine of t, end parentheses. Like we've established thus far, I'm saying that x is some sort of function of a cosine of t. I'm leaving room for the fact that there's other details we have to fill in. What are those details, or what do I mean? I mean that I hate my device right now. Oh, no, I mean, maybe I like it again. It's such an emotional roller coaster, really. I mean, well, here's what I mean. I want to test it. Like the whole point of a guess is to test it. Like I might be ready to test my guess right now, but I'm not really, because I'm a scientist. And I look at that cosine of t and I say to myself, wait a second. Okay, yeah, cosine, I like the idea of cosine, but I, as a scientist, cannot take the cosine of t, because as a scientist, I believe in measurements. I believe that all these t values are not just random numbers, but they're measurements that come from the lab that have units like seconds or minutes. And you cannot take the cosine of a minute or a second. You can take the cosine of an angle measured in degrees, if you like, or radians, if preferred, but you can't take the cosine of a time. You can only take the cosine of a section of a circle. Like the units are wrong. So what that means is if we even have a chance of making our cosine function work, we're going to at least have to, and this is for real. Again, I'm saying this, we will write this down and maybe you can, I'm saying you can't even take the cosine of t unless you first multiply t by some kind of constant, some kind of unknown arbitrary numerical constant that specifically and explicitly has units of radians per second. That is what I'm trying to say right now. It's hard to write down. I'll try to write down in a second. But I'm saying cosine is our guess. Cosine of t is an incomplete guess. It can't be right unless we say, it can only be right possibly if we say cosine of something times t, like something in the parentheses, the little parentheses that go around the t. We're going to have to put some letter next to the t, like lowercase a or lowercase b or k or c or something, some letter that stands for a number that we'll ultimately get or something, but that we don't know anything about, but we know it must be there because something with units radians per second must be there in the parentheses so that the per seconds can cancel out the seconds of t and leave us with just radians in the parentheses. That's what I'm arguing right now. And like that's a scientific argument. But again, it doesn't prove, it just means if we're trying to build a guess that we want to use, we better stick something before that t in order to make our guess even valid. And the thing that we're going to, so it could be any letter, right? It could be a, lowercase b, or it could be a squiggle. But in fact, for the benefit of hindsight or from history, the letter that physicists tend to use is lowercase omega. Okay, again, we could have used anything, and we don't have to know anything about omega yet. It's just a placeholder. But I'm going to say that we're going to put that placeholder. But omega, whatever it is, lowercase omega, which looks like a little w, stands for some constant with units radians per second. Oh, here we go. I think. Hello? Okay, what I'm saying now that you might want to write on your piece of paper, I'm saying that our new advanced guess from units from physics is x equals cosine parentheses omega times t. Omega is a new letter that I'm introducing now for the first, I know some of you have seen it on the web and blah, 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 but I'm saying in terms of this class, I'm now for the first time introducing the letter omega. I'm saying omega is just a constant that right now at this moment, the only thing we know about it is its units. Its units are radians per second. And that alone is like why we think it has to be there. And that's all omega is standing for the moment, is some unknown thing with units radians per second. Okay, here we go. Finally, sorry. Okay. I don't know. hold on. So where I am is, sorry. Oh no, you're kidding me. Wait, sorry, excuse me for 1 second. Oh yeah, okay. Okay. I'm saying this. Okay, this is where we are. All right, this is where we are right now. Sorry about the whole board thing. So just to back up 1 step, I'm saying based on data that you actually get in the lab or that you can picture in your mind, we're guessing that x is some function of the cosine of t, right? But then I'm saying now, since we're using science to unpack this, and we only care about it in the first place because of science, we need a constant next to that t to ensure correct units. That's what I've been trying to say. That is what I'm saying now. So now I'll say we're going to, so that constant has to have units of radians per second. So we could call that, we're just going to give that constant a name. It's a placeholder now. We're going to call it omega because that's what physicists do. And there are reasons for that. And I'll get into them, but it doesn't matter. I want to emphasize again, we're just building something here. So we put that name. So now what I'm guessing is in the red down here at the bottom is something like x equals cosine of omega t. But now you'll notice, obviously there's some other things written here too, because once I do that, I'm almost there. I'm almost good. Like I'm almost ready to check my my answer. But I realized, well, I'm still not done because talking about units, well, once you take the cosine of something, you get a dimensionless answer. Like the cosine of, oh, should I do this? Should I do this just to see if I ask what's the cosine of 60 degrees? Does anybody want to answer for 50 points? It's cosine of 60 degrees. Just wondering, anybody remember? No, put in the chat. Cosine of 60 degrees. Go once. This is just an example to see if we're awake. Cosine of 60 degrees. Anybody wants to put in the chat? Free 50 points, free whatever points, free 75 actually, because it would be the cosine of 60 degrees. Oh my God, I'm getting nervous. Cosine of 60 degrees. Sweet, sweet. Oh, I like how, oh, wow. Oh my God, all of a sudden it's like a, yes, great, fantastic. I love you people. Did I say that? Am I allowed to say love on Zoom? Sorry, I mean it in the physics sense. Wait, and the chat just disappeared. Yes, all of you put, oh, and one very good guess, Amanda. Definitely. By the way, every single one of you. Okay, so some people wrote. So the answer is 1/2 or 0.5. But please understand again, Rachel, Amanda, Billy, and Isabella. All of you should definitely submit what you just wrote, not just for the 50-point thing, but for the 75-point thing. That's like right or wrong, right? You just had the guts to actually say an answer to something, and you just risked potentially being wrong. And I'll even say that, yes, Amanda, I think you're actually like not right. I think that's cosine of 30 degrees, but that's awesome. That totally shows you totally get the question. You know your trig. That's 75 points either way. But okay, why am I? Thank you for paying attention, you for everybody. But okay, why am I bringing this up? Because notice every one of these answers, certainly including Amanda's, but every one of these answers that's in the chat is not missing any units. Like when Rachel wrote 1/2, she didn't write 1/2 meters, and that's not because she's being careless. Like the cosine of 60 degrees, right, is not 1/2 meters. It's 1/2. I mean, and it's also not 1/2 degrees or 1/2 radians. Cosine spits out a dimensionless answer, like on purpose. I mean, that it's actually giving you a coordinate on a graph. It's not giving you a measurement. And so that means we're still not done. If we could have this cosine omega t thing perfect, but the best but put another way, that cosine omega t, the greatest value it's ever going to give us is 1. And the lowest value it's ever going to give us is -1. But if this is supposed to be a function that tells us like where the mass is on the spring, we never said that our mass was only allowed to oscillate between 1 meter and -1 meters. In fact, in our case, it never even gets to, well, in our case, it goes from 0.15 meters to -0.15 meters. But you should be able to imagine any spring you want, doing any number you want, going from 1.5 meters to 1.5 negative meters. But the cosine doesn't do that for us. The cosine doesn't even give us meters at all. So what we would presumably have to do, if this thing even has a shot of being right, is we'd have to take that whole cosine thing and multiply that whole phrase by some other arbitrary constant, some constant for which we know it has to have units of meters. But the thing is, once we start thinking like that, like, oh, we need a constant that has units of meters. Oh, we actually already do have such a concept in mind. Like if you think about it, x naught, the number of meters that the thing was at when time equaled 0, that's precisely the constant that actually we're looking for here, if you really think about it, because cosine of 0 is 1. So when time equaled 0, right, then the whole cosine piece yields 1. But when time was 0, we didn't think our mass was at position 1. We thought it was at position some number of meters. What number of meters? X naught. Like that's what X naught is, whether it's 0.15 meters in our particular case or whatever. X naught is the position measured in meters that we're at when t equals 0. So that will work perfectly if we just put an X naught. I hope everybody's seeing this. Like if you plug in 0 for t, X will be whatever that X naught is, because everything else will turn to 1. So what I'm saying then is we have a workable guess. I don't know if it's a right or a workable conjecture. I have not proven that it's right. I haven't proven anything, actually. I'm just showing a way of thinking so that I'm just showing that we've built up a plausible, reasonable, formally dealable conjecture. And that's what we need, because now our job is just to test that conjecture. And if it's right, we're psyched. And if it's wrong, we'll do something more. And by that, of course, I wouldn't be wasting your time. The truth is, it is a correct conjecture. You'll see in a minute. Like, I'm not wasting your time with the wild goose chase. I'm wasting your time some other way. Before I turn the page, and I'm about to turn the page, and I think we are on page now, I hope. But before I turn the page, what was I just going to, I want to make very clear what we now have to do. I say we now have a guess. This is like that point 2 days ago where we had a guess that if dx over dt equals 5t, is that what it was? Yeah, we guessed that, or we did separation of variables, and then we started to believe, oh, x equals something times e to the 5t. Then our job was to differentiate. Like that's what we're going to do now. Like if this is right, we're going to find out once we differentiate it. But I have to warn you of one other thing. One other reason we're going to differentiate it, and we did this Monday and Wednesday, even if we didn't realize it. On Monday and Wednesday, we first got something like we did a power rule or whatever, or we got an E or something, and then we had to stop and use our information. We had to, once we were getting there, we were almost done, we had like an arbitrary constant in our answer. It was called C then, or it was called squiggle then, or it's being called omega now or something. But we had an arbitrary constant and we had to solve for that. And we were able to, when we differentiated and checked, we were able to, as long as we used the other piece of information we were given, the information about X naught. That's how and that's what's going to happen here. I'm saying now, and I know we're almost out of time, but we have one last thing to do. And you'll see all what we're doing right now. Once you open up, you'll see that the math methods homework, hopefully will seem a lot easier, make more sense once you see this. But I am saying our job now, we now have something that's plausible. So we're going to have to verify it by differentiating. I look like Bill Clinton doing that. Sorry. No, I don't look like Bill. I look like Bill Clinton before. Anyway, we have to differentiate in order to verify, and we have to differentiate or something in order to solve for the arbitrary constants. Like I'm saying x equals x naught cosine omega t. That's my guess right now, but that's not a complete or final guess, even if it's right, if I don't know anything about omega. Like I'm going to have to find out what I mean by omega. In other words, I'm going to have to write it in terms of things I do know. Otherwise, we're not complete. That's what we're going to do right now, and that'll be it. And that's so Yeah, so that's what this board said. Oh, sorry. Okay, so this board just says what I just said. Like our current conjecture is x. So our current conjecture is x equals x naught cosine omega t. If any of your internet connection suddenly gives out, or suddenly your computer is like eaten by a wild elephant that comes in from the Bronx, because that happens all the time, I want you to know we are now going to test this conjecture because we have to, because it's like the whole point of all this, and we're going to solve for constants. But just so you know, like this conjecture is correct. Like if we all like leave each other right now, like that is right. But okay, how do I know? Oops, sorry. Well, right. I have to make sure it's correct. What do I mean by it's correct? If it's correct, it means it satisfies. If this thing is correct, it means it's an expression for x that actually meets the conditions of the original differential equation. Like if this x is correct, that means that when you take the derivative of it with respect to time, like what it if we're correct, it means when you take two derivatives of it, you will get back itself. Like if you take this, if we're right, this differential equation says that we have found a function which, when you differentiate it twice, you get back itself. Like that's what this is saying. That if we differentiate this function twice, we'll get back itself, but times some constant times a negative. As long as we get back it, as long as this function does that, as long as this cosine function that we're guessing will spit back itself after we differentiate it twice, but times some constant times a negative, then we're good. And then we just look at what the constant's doing. I hope that sort of makes sense. And because we only have 4 minutes, that's precisely what I'm going to do right now. I mean, in principle, this is what you do, but this is what I will do. So this is what I will do right now. But so we're going to like in the 4 minutes we have, just to make this program clear, because all of this is, I'm trying to make this as like step by step as possible. But I want to constantly acknowledge what we're doing is like a kind of backwards thinking. We are taking the old process of differentiating and trying to think about it backwards. So it is a little bit, it takes some getting used to. But our job is to differentiate twice to see if we get back that original function, and differentiate twice in some manner that allows us to see something about omega. Like I don't know what omega is other than radians per second. If I can't find out somehow, then this is useless to me. So again, I know we have like 3 minutes, but here we go, and then we're done and blah, blah, blah. And again, just do whatever next homework you're up to. Like if you're up to math methods, please try to do that for Monday. If you're past it, give the next homework a shot. You may or may not be able to do, but whatever, just like wherever you are. But here we go. We're testing this. I'm going to do just a little, so I'm just, yeah, I know we have 3 minutes, so I'm just going to, so how do we test? We differentiate, and then we differentiate again, because this is a second derivative. So I take the first derivative of this, like I'm just going to do this because but I take the first derivative of that expression. So it's a trigonometric expression of a function. So it's going to be chain rule. Well, you may have to think about this depending on who you are, but I'm saying this is what and I'm writing it in like a physics way. I'm bringing the omega to, but basically it's negative sign because the derivative of cosine is negative sign, but then since it's actually cosine of omega t, I have to multiply my whole answer by the omega. So that because of chain rule, right? So I got that. Again, please ask me questions about that next time if you wish. But for the moment, please forgive me for just doing this. But now I'm supposed to take the derivative again. I didn't take derivatives again yesterday or Monday, because that was only a first order differential. But here we have a second, so I have to take it again. So I just do it again, chain rule and all that. But I get this time, right? Like I'm looking at the time. Like remember, derivative of cosine is negative sine, but then derivative of negative sine is negative cosine. Like the negative sign did not go away, not because I'm being careful, it did not go away. But do notice what happened. Oh, like, oh, wait, this is looking good. Like when you take the derivative of cosine twice, you do get back negative cosine, right? That's what we sort of wanted. And look, that's what's happening here. We're getting back. In fact, we're just about done. But if we right, if we just rewrite it like multiplication is commutative, if we just rearrange it a little bit, we notice, oh yeah, this whole business here, that's what we were guessing to be x. So indeed, the guess we made does look good because when we differentiate it twice, we got itself, like that's itself, x, times some constant, granted a weird constant, but some constant, omega squared, times a negative sign. Oh, yay. That's what we wanted. And we're just about done. I promise, I promise, I promise. Like that's really good news that we got back the original function times some constant, because the original differential equation said that's what's supposed to happen. If we have a proper solution, that's what's supposed to happen. The only thing is the original differential equation said this, and we just found this is like the last board, I think. It's 4:21. Anybody who has to go right now. This is really the last line. I'm going to pause and see if there's any questions or whatever. I can do that. So I'm not rushing, but you definitely can. But we are done. But what I'm saying is what we just learned, what we just showed ourselves is that x equals x naught cosine omega t is a solution, like is a solution to this problem. It is, as long as we realize that by omega, that thing that we just put there just to satisfy units, omega must be the square root of k over m. Like k and m were original givens. They're constants we know. Omega apparently is the square root of those constants put over it. I mean, just looking at what I just did here. This solution works if and only if by that omega thing that we just made up, if by that what we really mean is square root of k over m. In other words, the answer to this whole thing, and again, please leave if you have to, but this is, but the answer we're saying, therefore, to finally wrap up the homework 1, question 9, we're saying, and I know many of you put this in your homework, maybe from the web, and maybe some of you understood it more than others, but it's totally true. But I am saying, yes, this is true. If we were looking for some kind of function into so as many of you did do, I'm just now saying, fine, I agree that if you ultimately say x equals x naught cosine of square root of k over m times t, and if you plug in all the numbers that were given in question 9, homework 1, then yes, then finally there, that's what you can plug in those numbers to get an answer for x. And I think the answer you get is 0.116, and that's correct. But what I'm hopefully have just done is shown you why that's like that's a lot, but that's why that works. Like that's where that comes from. That is the equation of motion for a simple harmonic oscillator, like for all time. Like in a way, it's a memorizer now. We're finally like, that's a conclusion. And that's the end of class for the moment. Thank you for waiting for so long. Like, obviously, then you look at wherever you are in the homework, and I think you'll start seeing how things apply. But you definitely, whenever there's a K or M anywhere in your homework, you can now believe omega equals square root of K over M. Like, that's a takeaway from this. But okay. Oh, thank you. Have a good afternoon. I'm just going to wait here just to make sure that there's no questions or anything, because I know I rushed that. But I'm good. If you guys are good, you guys are.
Have a nice day.
Thank you. You too. Thank you. You too. Thank you.
Thank you, Professor. Have a nice weekend. See you Monday.
Yes. See you. Oh, Monday, right? Yes. Great. You too. Thank you. And thank you. Thank you. Goodbye, Lydia. Goodbye. I love you. You guys are good. Thank you. Thank you. Thank you. Awesome.
I know I'm still here. I'm just trying to get it.
Oh yeah, yeah. Okay, no, I'll just yeah. Take your time. I'm absolutely.
Where did the negative sign go?
Oh my God. Oh, really good question. Like, really good question. Well, right. It's not a mistake. Like, there won't be a negative sign in this final answer, because where the negative sign went, hold on, I'll show you. Well, where the negatives, how can I put this? The negative sign, like, we're saying X equals something that doesn't have a negative sign in it, because like X equals cosine yada yada with no negative signs, because when you take the derivative of cosine, you get negative. Oh, wait, I'm sorry, what?
Oh, no, I was saying the same thing. You get a negative sign.
Okay. So yeah, like cosine works because it produces a derivative that has a negative sign, and then the second derivative still has that negative sign. So in other words, what we're saying is, oh yeah, we're saying it's true that we're saying this negative sign is honored.
Oh, in the second derivative. Like, it's already there.
Yeah. Exactly.
Okay. Okay.
And should I go back to the other?
Okay, I got it. Thank you. Bye.
Thank you. The best. Take care.